All right, but today's problem is combination sum. This is a medium, and it's our first backtracking problem, which we'll talk about what that means momentarily. Let's take a look at the prompt, and then we'll talk about how this relates to the approach. Okay, so you are given an array of distinct integers nums and a target integer target. And your task here is to return a list of all unique combinations of nums where the chosen numbers sum to target. And they clarify something really important for us here. The same number may be chosen from nums an unlimited number of times, and two combinations are the same if the frequency of each of the chosen numbers is the same, otherwise they're considered different. Okay, and we may return the combinations in any order, and the order of the numbers in each combination can be in any order. So we're going to return like a list of lists, I think. Let's take a look. Yeah, a list of lists. And it doesn't matter what order those lists are in, nor the numbers in the lists themselves. Great, so as an example here, if nums is 2, 5, 6, 9, and the target is 9, obviously one of the very easy solutions to that is just pick 9. But notice another combination we can pick is 2 and 2 and 5, which sums up to 9, and even though there's only 1, 2 in this array, we're allowed to include 2 of them, or as many as we want, really. So if we had like 3 in here, then we could pick 2, 2, 2, 3, and that would be a valid answer, right? So as many times as we want to pick or not pick a number, we're allowed to do that. Okay, another combination here, and you can see this blows up really, really quickly for certain combinations. If we have 3, 4, and 5, and the target is 16, we can pick 4 3s and a 4, 2 3s and 2 5s. We can pick 4 4s. We can pick a 3, 2 4s, and a 5. And then there are some scenarios where we simply cannot make the target, no matter how many of each of these elements we pick. And in that case, we just return an empty list because there's no good combinations. So it's a list of nothing. All right. I just realized I don't have chat open. So let me open that really quick. Okay, sweet. So that's the problem. Some constraints they give us. All elements of nums are distinct. If they weren't, we could make them distinct pretty easily. That'd be just O of n time complexity. Nums.length, so the number of nums that we could be dealing with are between 1 and 20. The numbers themselves are between 2 and 30, so we don't have to deal with negatives. And then the target will also be between 2 and 30. Okay, so the number itself is not going to get super huge, but as you can see, even with just a number like 16 and 3 options for nums, it's still quite a few options and quite a few elements in those options. So like I said at the very beginning here, this is a backtracking problem. And what backtracking means as a whole is we'll kind of proceed down a path until we know that it's not going to work out any further. Then we'll back up and proceed down another path. You can think of this kind of like a depth-first search. The idea is like go as far as you can until you know there's not a good solution further down the line, then back up and make one small change, and back up and make one small change. Ordinarily, we actually think of backtracking as like a very naive type of solution, but there are some problems for which, like this one, it's just the best that we can do. So yeah, the question is what do the paths look like? What does it look like to exhaust a path? And what does it look like to switch to a new path? Well, let me think. This is going to be a recursive solution. The question is like, how do you set this up so that each layer of recursion has enough information to make a good decision? Which is unfortunately quite tough for this one. I was just telling someone actually the first time I did this problem, I spent like days on it and was just like, I don't know what's happening. So hopefully this explanation clarifies it a little bit for anybody watching. Okay, so let's take the example actually, and this is insane because like I'm going to take up, if I do the whole example here, pretty much the whole damn page. So give me a sec to orient this the way that I want it to be oriented, maybe. Okay, so this is going to be real wide. Okay, so here's the core of the idea here is since we can take each number an unlimited number of times, there's a very reasonable stopping point. So the example was 3, 4, 5 with a target of 16, right? So let me just jot that down so we can refer to it. Okay. Now, there's some very easy stopping points if you think about what it looks like to take one single number repeatedly. So like if you're just taking threes, then you could say, okay, what if we take 1 3, 2 3s, 3 3s, 4 3s, 5 3s? As soon as you hit 6 3s, you're going, well, that's too big. There's no way to get back to the answer from here, right? Now, the backtracking idea here, so we'll do this kind of manually. The backtracking idea here is, okay, now that we know that this is too big, let's back up to here and see if we can add on a 4. Well, that's too big, so we can back up to here, just 4 3s, right, and add on a 4, and this actually gets us one of the answers, right? And so we would mark this down somewhere. 3 3 3 3 4 is one of our answers. Okay, now obviously there are more elements in here, so we might say, hey, well, in fact, you know what? Let me back up because I didn't give a complete answer here. At this point, we say, hey, maybe I could use a 4. That's too big. Okay, well, maybe I can use a 5, right? And that's too big. So now we unfold here. We go, maybe I could use a 4. So as you can see, there's many options, but the core backtracking idea is like take as many of this number as you can, and then back up and see if you can fill in the gaps with other numbers, right? And eventually we get to a point, if we continue that process, where we go, hey, let me just start with a 3 and take as many 4s as I can. So we'd like to here. Yeah, exactly. So I guess in terms of approaching this programmatically, right, we want to say, let's exhaust all the ways to take 3s. And then we'll start considering all the ways that we can take no 3s and just take 4s and 5s, right? So this, this is too big. We go back here. This is too big. We go back here. This is too big, right? Or actually, no, this is one of the answers, right? So the question is like, how do we do this programmatically, or how can we like set up the recursion so that we follow down one path as far as we can go, right? And then also, how can we detect when we are kind of out of numbers to try, right? And here's going to be the system that I propose. This is the only one that makes sense to me for this problem, so there might be other ways to do it. But here's the one that I propose. Well, so here's the problem with a double for loop. What if there's 10 numbers? How do we know how many 4s to include, right? So there isn't, I mean, we would have to set up a whole lot of crazy stuff to be able to say, I do want to do a for loop, but for each of the numbers, and I want to make all the possible combinations until they're too big. We want to have some way of being able to just like have the function do it for us, so to speak. And so here's the system I'd like to propose, is that we can create a tree. Okay. Now each node in this tree, it's not going to be a literal tree that we're going to construct as an object, but we can think of the decision making as a tree. And each stop along the way is going to have an index. And that index tells us which number we're considering right now. Okay. So we start by saying, hey, the list under consideration is an empty list with I equals 0. Okay, if we go left, what we're going to do is keep the index the same, but add the number at index 0. Okay, so actually let me make this look a little nicer. Okay, and then if we go to the right, what we're going to do is we're going to say keep the list the same, so don't add anything to it, but start considering the next index. Okay, and hopefully, even with just that, it becomes clear we can consider all the possibilities just by following this structure. So going left in this tree means add a number, and the number we're going to add is whatever's at the current index. Going right in this tree means keep the list the same, but start considering the next index. Okay, and so one of the exhaustion points for this backtracking tree is somewhat obvious immediately. If you get to the point where the index is too big, it refers to something that's not in the list. This is kind of what we might consider like a failure-based case. You can stop, right? There's nothing else further on this branch of the tree. But for all the rest of these guys, we have an entire like other subtree to explore, right? That begins with the number that we're looking for. Okay, now the 3 tree is actually huge because we have many layers here. So again, going left means add another element from the current index. Okay, so 3, 3, 3, 3, 3, 3, 3, 3, 3. And you'll never guess what comes after this one. Okay, and so what I'm trying to get us to is a point which we would consider another failure point here. So as soon as we get over here, we add on this 3. The other failure point we can consider is, hey, what if the sum is too big now, right? This would be, and I'm going to mark this one in orange, failure because the sum of the elements is beyond the target and there's no way to get back, right? This tells us you don't need to keep doing that, but going down that path, you can back up and consider a different option, right? Okay, so as you can see, the tree is gigantic, and I haven't even begun to fill it out. I think we're not even like an eighth of the way through the whole tree here. So anyways, basically for each of these nodes, so to speak, or each of these decision points, we need to consider, hey, what if I add one more, which might fail, right? And if once I've considered that, I can say, well, what if I will start using a number from the next index? Okay, this represents what I talked about earlier, which is, oh, I've erased 1, 3 from the list, and now I'm going to consider what it looks like to add a 4. Now again, this one is too big, so this is another like the sum is too large failure point. And we'll completely exhaust this entire subtree here. So now we say, hey, we tried adding 1. It didn't work because the sum was too big. So let's increase the index. Do it again. This is now 3, 3, 3, 3, 3, 5, which is again too large, right? So we go to the right one more time here. And the reason we stop here is because at this point, the index becomes too large. And this is our like index out of range failure case. Okay, and then we're going to do it for this, and 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 eventually we'll have this whole tree complete, right? And we will have considered all of the possibilities in the tree. This is not really, this is like a small fraction of the total considerations we have to make, but as you can see, all of the possible combinations, even just for these 3 numbers, are gigantic, right? And this is why it's preferable for us to kind of do this recursively, because God, how else are we going to make all the numbers work together the way we need to? And to my knowledge, there isn't really a more efficient way to do this. This is on the scale of like, this is exponential growth for sure, which kind of sucks, but it's the best we can do in this case. Okay, so let's think about this. Basically what we need to do is for each time we recurse, we have to consider 2 options. What if I add on 1 more of the current number? And then what if I don't, but I start considering the next number? Okay, that's the overall vibe. Now let's talk a little bit about time complexity, just because I want to see if we can get through this somewhat quickly, because I think this could drag on forever and ever. One thing we would rather not have to do is manually add up all the numbers every single time, right? Now, since we actually know what we're adding on every time, what we can do is we can also capture like a running total. So when we start, it's 0, and we can pass that along to the next guy that has a running total of 3, and then 6. And so all we have to do is take the previous total and add on the current number when we go to the left, right? And then when we go to the right, the sum stays the same. Okay, so this way we don't have to like keep repeating the addition. Yeah. Yeah, so the information that needs to be passed along level to level is like, what's the current index we're looking at? What is the collection of numbers that we have at this stage? And what is the sum of those numbers so that we can quickly calculate what it is after adding a number or after moving the index. Okay, am I going to be able to do that in code? Your guess is as good as mine. We're about to find out. Let's give it a shot. I'm going to just like include, oh, there's me. There's me as a little baby twink. Okay. Oh, you know what? Something I should have mentioned. They didn't tell us that nums was sorted, but the time complexity here is so massive and disgusting that we can go ahead and sort, and it does not really affect our time complexity. So we'll do that. One reason we want to do that is just because we want the, well, you know what? I don't think we have to, huh? Yeah, I don't think we have to because we're going to, like, if this was 354, we would have considered all of the possible, like, combinations anyways, huh? So no need to sort. We would need to deduplicate, or I guess we don't really even have to deduplicate here. So this approach is quite resilient when you think about it. The only thing that I guess we would want to make sure of is that we don't duplicate like entries like this. We shouldn't because, one second, I'm being called by a friend. Give me 1 second to fire off a text and then we'll go for the code. Okay. So, yeah, in order to make sure that these aren't duplicates, what we can do is we can store these guys as a set of tuples first, which is going to make sure that, like, if we accidentally encounter some duplicates, they won't be duplicated. And then at the end, we can convert that set of tuples to a list of lists. So internally, or like as we go, we'll store it differently. At the end, we'll just make sure we give them the format that they want. Okay, so we're definitely going to need a helper function here because we're passing some additional information. Say definition combination sum helper. We need to give it an index. We need to give it like a running sum. And actually, now that I think about it, the list itself, it just mutates as we go. There's never going to be like, if we don't thread this, assuming we don't do threading, the list is only ever going to be accessed by like one decision at a time, right? So we can just have the like value list be a class function. Isn't this supposed to be colored? Why didn't that highlight? Anyways, it's an empty list at first. Note we can't have this be a tuple right now because tuples are immutable. So when we need to store like a collection of numbers, we'll store it as a tuple, or we'll convert like the current list to a tuple. And then what else? Is this it? We need self dot combos, I'll say, is going to be an empty set. Okay, and then what are we going to do? We're going to run combination sum helper using index 0 and a running sum of 0. And then we're going to return, so this is not the actual problem part, but just setting up some of the like logistics. Sorry, now I'm like having 3 conversations at once all of a sudden. So what we're going to return here is I think it's this. So turn the set into a list, and then each element of the list is going to be list from the tuples for tups in combos. Oh, actually, I don't know why I've converted it to a list like that. We can do this. Yeah, this I think is probably the best way to do it. So return a list that has the tuples as lists for each tuple in combos. So not tups, but tup. Okay, so what is the helper function going to do? Well, it needs to explore the left possibility and the right possibility. One thing I want to note here is that the target will be between 2 and 30, so we're never going to start with an answer. One of the questions is how should we, should we consider that we've got a right answer here or after we've passed it along? I guess the running sum is going to be after inserting an element if we have inserted it. So I'll say if running sum equals target, then what can we do? We're going to convert value list to a tuple. And then we're going to store that in combos. You know what? It's kind of funny. Technically, it's not combinations, it's permutations, isn't it? Because the order matters. I'm going to call it perms, just to be proper here. Okay, so if we've hit the target, then you can add this, and also you don't need to explore any further, right? So for example, I don't know what that means. So when we hit like 3, 3, 3, 3, 4, that is an answer, and there's no way to get another answer by adding more 4s or by adding more of the next number, right? So at this point, we can actually return. Okay, so assuming that we didn't get a correct answer already, what do we need to do? Well, we need to go left, and when I say go left, geez, so many things happening right now. Okay, so when we say go left, what do we mean? We mean add on another entry. So this would be self.valueList dot append nums index, and then call combination sum helper with the same index and a slightly increased running sum. Right? Okay, so if there's another answer somewhere to the left, this will capture it. Right? And then if there's another answer somewhere to the right, we'll capture it with combination sum helper index plus 1 with the same running sum. And actually, low-key, that might be it. Is that it? What the hell? This is, I thought the code was longer than this. I'm tripping out right now. Is that it? Oh, no, at some point we need to remove. Okay, so hold on. After you go left, right, so like, let's say we're stepping back from here to here, you need to remove the last element, right? So self.valueList.pop. If you go right, so if you backtrack from the right though, nothing happens because you were just considering, like, the index was passed as part of the function, right? So the list stays the same. The running sum was passed as part of the function. So I think that's it. I'm just running through logically like anything else that we might need to change, and I think that might be all, which is kind of crazy. All right. Let's take a look and see if it runs. Oh. Whoops. Oh, you know what? We forgot the other base case. The other base case was if index is greater than or equal to the length of nums, then we can return. Okay. Oh. Oh, you know what? We also forgot the so I only considered the success base case. The other thing we need to say is if the running sum is too big, then there's no answers further down the line, right? And actually, this is making me realize we should sort it. We should sort nums, and this is because if we have it out of order, like 3, 5, 4, then if we fail at 5, there might have been an answer further down the line that used 4, right? So right here, we'll say like nums.sort, and let's see if this works. Self.value list. Okay, so I have a bunch of syntax errors because of who I am as a person. And great, there we go. Great. Hey, guys, I feel so good about that. This problem used to kick my ass. And there we go. Yeah, I guess that's all I got to say about that. um, let's see what my old solutions used to look like, because I feel like it used to be way more code than that. Yeah, the last one I accepted was over here. No, it's about the same. Oh, actually, this is way shorter. Oh, no, this is about the same. Yeah, I just put these on the same line right here. Oh, yeah, and see, I actually like the logic that we did better here because this is very like, if it's greater than or equal to, do this, but then if it's equal to, do that. I don't like that, like nested logic. And then, ooh, I did some weird stuff here with the pop. I think I like the like organization much better for what we decided to do today. So yeah, she's pretty good here, and this avoids some of the pitfalls like having to continually calculate the sum of the current list. Library would be closing soon, so I got to get going. But yeah, that's what we got. Any questions? Hey, thanks. I hope you guys have a good break too. Appreciate you tuning in, and we'll be back to it December 1st. Have a great Thanksgiving, and yeah, see you then.